Today we are going to talk about distributions and their means. So you might have heard of the normal distribution, probably the most common distribution. This is its density function with two parameters mu and sigma. Mu is the mean, sigma is the variance. And what is the mean of this distribution? It is just mu. I mean, that's the definition. So, okay, the normal distribution has a mean of mu. Now let's look at the Cauchy distribution. The Cauchy distribution, this is the probability density function. And what is its mean? The mean is undefined. So you would think that the mean would be zero because the distribution is symmetric, right? So if you imagine a y equal to x line, there would be a positive integral on the right side and a negative integral on the left side, and the two should cancel out, just like they do with the normal distribution, right, for the left and right side of mu. But no, it's not zero, it's undefined. And then you have something like the f distribution. Here is its probability density function. It is some complicated terms, a beta function down here. And what is its mean? It's d2 by d2 minus 2. It has two parameters, d1 and d2, but only when d2 greater than 2. If d2 is not greater than 2, then the mean is not defined. Now, what if I told you that you can take one look at this complicated beast of a probability density function and reach this conclusion within a few seconds? And similarly for the any other distribution, if you just look at the probability density function in a few seconds, you can tell does it have a mean, and then does it have a variance, and so on. And then for the normal distribution, it's going to have all moments. It's going to have a mean, a variance, a third moment. You can tell that very quickly as well. So how do you do this, right? So you kind of look at the PDF. You start with the PDF, and the question on whether the distribution has a mean or not. The thing is, you can ignore a lot of the complexity. So this normalizing constant, all of this stuff doesn't matter. What really matters is how the function behaves when it becomes really large, when x becomes really large. And that I call that the tail behavior. Probably other people call it the tail behavior too. But the tail behavior is what's important in telling you whether it's going to have a mean or not. So to get the tail behavior, like I said, you make x large, and you can imagine that as x literally becoming large. You start with the PDF, just make x large, remove the terms that can't keep up with it, and you're left with the behavior of the function only for very large values of x, which for the case of the f distribution becomes 1 divided by x to the power 1 plus d2 by 2. There is no d1 parameter. It had only two parameters, d1 and d2, and so that the question of whether it has a mean or not depends only on d2 and not on d1, and then you can make other assertions as well. So like I said, for the f distribution, this is what you're left with. Now what about the mean, right? Like how do you use this to reach the conclusion that it has a mean only when d2 is more than 2, right? So well, for the mean, we know that let's switch to somewhere we can write. So it's basically like if the PDF of the function is f of x, of the distribution is f of x, then the mean mu is integral f of x dx over the domain of the distribution. So in the case of the f distribution, I believe it's 0 to infinity. 0 to infinity. So and then for the normal distribution, it would be minus infinity to infinity, and so on. So now like I said, you only care about this function, the way it behaves. Oh, I'm sorry. There's an x here as well. It's the mean is x times the PDF dx. Now the only thing you care about is how this function behaves when x becomes really large, to determine if the mean exists or not, right? If you want to calculate the mean, you want to know what it is, then you have to take all the complexity into account. But if you just want to tell whether is going to exist or not, you can get rid of a lot of the stuff. Only consider the tail behavior. Like we said here, the tail behavior was 1 by x to the power 1 plus d2 by 2. So then, this kind of pseudo mu, so let's call this mu tilde, becomes integral x times, in place of fx we have 1 by x to the power 1 plus d2 by 2 dx, which is the integral of dx upon x to the power d2 by 2, and from 0 to infinity. And you can see that as soon as you have a 1 by x, if you have something like integral dx by x, right, 0 to infinity, this is going to be log x from 0 to infinity, which is going to explode, right? It's not going to have, it's not going to converge to anything. If you have dx upon x to the power 1 plus epsilon from 0 to infinity, then you're going to get x to the power minus epsilon from 0 to infinity, which is 0 minus 1, and there'll probably be a negative sign there as well, and that will become 1. So that's going to not explode, right? It's going to, the integral is going to give you something finite. So so this integral over here, it converges only when this bit here is 1 or less, right? So it's less than 1, more than 1, right? When it's more than 1, and then you get into this scenario where it actually gives you something finite, and this implies that d2 by 2 greater than 1, which implies d2 greater than 2. And with that, you've reached the conclusion for the F distribution. The mean only exists when d2 is more than 2. Now, I call this function the kind of stripped down tail behavior of the probability density function, and you can think of the tail behaviors of various distributions, right? So I have a table here which kind of lists out the tail behaviors of a variety of different distributions, and you can see that a lot of them have very similar tail behaviors. So you can already tell that the F distribution, because it has a mean only when d2 more than 2, the Lomax distribution, which has a tail behavior of 1 by x to the power 1 plus alpha, will have a mean only when alpha is more than 1, right? And similarly, the T distribution, another very famous distribution, two sample T test, is going to have a mean only when this new parameter is greater than 1. So you can see a bunch of them end up having, these three actually end up having the same tail behavior, even though their probability density functions look very different. And then distributions like the exponential, the normal distribution, they're going to have all the moments. They're no matter what, first of all, the tail behavior doesn't even depend on any parameter. So it doesn't matter what they are, what the parameters are, they're just going to have the mean, have a variance, have everything. So yeah, now you know how to take one look at the density function, just explode the x, get rid of the riffraff, and tell whether it has a mean or not, a variance or not. Thank you.